Hello again, this is Professor Roman, and let's continue the lecture series Transition to Advanced Mathematics. We are talking now about combinatorics, which is a branch of mathematics devoted to counting techniques, the art of counting. We just discussed ordered arrangements of objects, in other words, permutations. Let us now take a look at unordered arrangements. If S is a set of size n, then an unordered arrangement of size k taken from S is nothing more or less than a subset of size k. Just grab k elements. Order doesn't matter, so it's just a subset. But in combinatorics, ordered arrangements are generally called combinations. They can also be called subsets. Combinations are arguably the single most important object in combinatorics. Here's the formal definition. A combination of size k is an unordered arrangement that is a subset of k elements taken from a set of size n. The number of combinations of size k taken from a set of size n is denoted by Cnk. To obtain a formula for Cnk, we can relate this number to the number Pnk, and we already have a formula for that. So, just as in an earlier example, each of the Cnk subsets of size k taken from a set of size n serves as the underlying set for a family of k factorial different permutations. So here's the picture. This is a combination of size k taken from our set. And if we reorder these elements in all the possible ways, there are k factorial different ways to order these k elements, in other words, k factorial permutations, whose underlying set is this set. As we scan through the underlying sets, obviously we get different collections of permutations because the underlying sets change. So for each underlying set, there are k factorial permutations. So when we take this product, we get all the permutations. And we can just solve that for Cnk. It's Pnk over k factorial, which is equal to n lower factorial k over k factorial, which is equal to this, which is a very attractive formula, n factorial over k factorial times n minus k factorial. This expression is denoted by this symbol. This is called a binomial coefficient, for reasons we'll see later on, and it is read n choose k, because that is what this number represents. It represents Cnk, which is the number of ways of choosing k elements from a set of size n, in other words, the number of subsets of size k. The binomial coefficients are, again arguably, the single most important numbers in combinatorics. I think that's a pretty safe statement. Here are the formulas. Then again, Cnk is equal to n choose k, which is this number. It's also equal to either of these, and here this is spelled out explicitly, the lower factorial. So we have two different algebraic formulas. Of course, they're equal for Cnk. Now, just to be clear on the notation, because this isn't always clear, at least in this book, CNK does not denote this number, this formula. It denotes the number of combinations of size k taken from a set of size n. This symbol is shorthand for this expression. So this is an algebraic statement. This symbol is this formula. This symbol you express in words the number of combinations or subsets of size k taken from a set of size n. So these are different concepts, but they happen to be equal in value. In the matter of actually calculating binomial coefficients, this formula is generally much better than this formula. And the reason is that the factorials grow very rapidly, and we want to avoid having to take large factorials whenever we can. And so this has n factorial in it. N is the biggest number between n and k, and that means n factorial might be difficult to calculate. This doesn't involve n factorial unless, of course, k is equal to n. So as long as k is relatively small, we only have k factors in the numerator, this can be much simpler to calculate, smaller number. And if you want to convince yourself of that, take out a calculator and try to compute this binomial coefficient, first using this formula. So enter into your calculator 100 factorial divided by 3 factorial times 97 factorial and see what happens. Then try to do this one using the calculator. Here are some simple examples of computing binomial coefficients. And here are some special cases that are worth memorizing. It's not as bad as it looks. You don't really need to memorize the first two. N choose 0 calculates the number of subsets of size 0 taken from a set of size n. Well, there's only one such subset, the empty set. So this is equal to 1. N choose 1 is the number of subsets of size 1 taken from a set of size n, and there are certainly n of those. This one and this one are worth remembering, especially n choose 2. You'll save a lot of agony if you don't have to, rethink what this formula is. Just remember it. Okay. Here's an example of the use of binomial coefficients in counting. A ternary word of length n is a string of zeros, ones, or twos of length n. So here are 2 ternary words of length 5. This one doesn't happen to have 2 in it, but there's no requirement that each of these show up. So it's a binary word of length 5 as well, but it's also a ternary word. To count the number of ternary words of length 12 that have exactly 7 zeros, 3 ones, and 2 twos, we perform 3 tasks. So we can use the fundamental counting principle. First, we choose 7 positions in the word in which to place the zeros. Then we choose 3 positions from the remaining 5, still open positions, in which to place the ones. And finally, we choose 2 positions out of the remaining 2 positions, so there's only one way to do that, to place the 2's. Actually, the point is once you've placed the 0's and 1's, there's no real choice left for where the 2's go. It's whatever's left. So by the fundamental counting principle, the total number of ways of performing these 3 tasks is 12 choose 7, times 5 choose 3, and then times 2 choose 2, which is 1, as expected. And that comes out to be 7,920. Even this simple problem should give you a sense that we are developing some powerful techniques here. If you had to do this by brute force, that would be a chore, considering there's almost 8,000 of them. So thinking is far better than just writing down as many as you can until you're exhausted. There's a really good chance that if you did that, you would miss some anyway. So here's another example. To count the number of subsets of size 2 taken from a set, this set S, which is 1 through 20, that do not contain 2 consecutive integers, we can use a very simple but often extremely useful idea. If we would just wanted to count the subsets of size 2 of S, it would be 20 choose 2. So that's easy. But when you add this condition that it doesn't contain 2 consecutive integers, a direct approach to this problem could be rather testy. But what you can do, and often, as I say, this is very useful, is count what you don't want and subtract it from the total, leaving a count of what you did want. So in this case, the total is the total number of subsets of size 2, which, as I said, is C22, which is 190. These are the number of subsets of size 2 of all types, no restrictions. What we don't want are the subsets that consist of consecutive integers. What do those subsets look like? Well, they look like k plus 1, where k could be 1, you'd get 1, 2 here. K could be 2, you get 2, 3. K can go all the way up to 19, you get 19, 20. These are the subsets you don't want, and there are clearly 19 of them. So all we have to do is take our 20 choose 2 and subtract 19, and we get 171. Okay. So again, I'll say, when you have to approach a counting problem, unless you get a sense of what to do right away, if you're not clear, always think about the fact that maybe it's easier to count what you don't want and subtract from the total. It's always something to give consideration to, because there are times when that is much simpler than a direct approach. A common counting problem is determining how many ways there are to partition a non-empty set into a certain number of subsets, non-empty subsets. And they're often referred to as groups. So for example, how many ways can 12 people be partitioned into 3 groups of 5, 4, and 3 people? To answer a question such as this, we have to first ask ourselves whether the groups are to be considered distinguishable or indistinguishable. And that's sometimes a little tricky. It's nice if the problem tells you whether the groups are to be considered distinguishable or indistinguishable, but sometimes that's not clear. So you either need to make that decision yourself and risk answering the wrong question, or you need to answer two questions, one when the groups are distinguishable, one when they're not. Okay. I'll bring that up again, but let me just first discuss this issue. How do you tell whether the groups are distinguishable or indistinguishable? Does it matter? It matters, and the way you tell depends on the context of the problem. Let me give you an example. Suppose that a professor decided to give out grades completely arbitrarily, so no exams or anything, by randomly dividing his 12 students into 3 groups, also of sizes 5, 4, and 3, and giving A's to the students in one group, B's to the students in another group, and C's to the students in the final group. These 3 groups are clearly distinguishable. All you have to do is ask one of the students who got a C, and his or her response is likely to be, well, I was in the wrong group. So they are obviously distinguishable groups. So even if the problem doesn't say explicitly the groups are distinguishable, the context tells us that they clearly are. On the other hand, if the purpose in partitioning the students into these groups is simply to place each group of students in a separate room, but separate identical rooms, to watch the same video lecture given by the same strange but brilliant professor, then it doesn't matter which group goes into which room. The rooms are identical, the video's identical. So in this case, the groups may as well be indistinguishable. Another way to view this is to note that when the groups are distinguishable, as in the grade-giving scenario, it matters which group a given object, a student in that case, belongs. Whereas when the groups are indistinguishable, as in the video scenario, it only matters which students are in the same group. So if you, for example, were a student standing in the hall and you had to choose between the 3 rooms, you wouldn't care which room you went into because the groups are indistinguishable. Now you may be thinking that the groups in this example in particular of the 12 students being placed in groups of 5, 4, and 3 are always distinguishable by their sizes, right? Since the sizes are different, you can always distinguish the 3 groups by their sizes. And that's correct, but that's not the type of distinguishability that we are concerned with. Groups are always distinguishable by their internal properties, unless, of course, they are the same size and have the same elements, then they're not distinguishable. But otherwise, you know, if you split up the students into 3 groups, and one of the students is named John, you can always distinguish the group that contains John by saying it contains John. So there are ways in which groups are always distinguishable unless they are identical, same size, same number of elements. Same elements, not just same number. What we are concerned with is whether the groups are distinguishable by an exterior property, not an external property, not an internal property. So the grade, for example, the grade giving has nothing to do with the people in the groups. One group gets A's, one gets B's, one gets C's. That is the distinguishing factor, the grade, A, B, and C. It's external to the internal properties of the group. To answer the question then that's posed here, how many ways can 12 people be partitioned into 3 groups? The issue of distinguishability is not addressed in the question. So you can take the attitude that the question is incomplete, which would be accurate because it doesn't tell you about the distinguishability, but that argument isn't going to help you. What you're going to have to do in a situation like this is solve the problem twice, answer the question twice. Once if the groups are considered distinguishable, and once if they're considered indistinguishable. So the burden shifts from a poorly written question to the burden on the person who's going to answer the question. You're going to possibly see such questions in this course, and it is done deliberately. The missing information is left out deliberately so that you will solve the problem both ways for practice. Okay. Usually, I can't say always, because I don't know, but usually distinguishable cases are easier to resolve than indistinguishable cases, because you have a little more information, a little more at your disposal. So for this particular question, we'll first assume that the groups are distinguishable. And we can do that by labeling them G1, G2, and G3. So in this case, we can reason as follows. The number of ways of choosing 5 people for the first group, which we'll call G1, is C12,5. Then the number of ways to choose 4 people for the group G2 is C7,4, because there's still 7 people left. And finally, there's only C3,3, or 1 way to choose people for the remaining group, G3. So the fundamental counting principle, which does apply, the independence is satisfied, is simply to take the product of these 3 binomial coefficients, or these 3 numbers, and we get 27,720. That's the number of ways of forming 3 distinguishable groups. So if we're giving out grades, we have distinguished the 3 groups. We can give the A's to group G1 or to group G2 or G3. We can give the B's out and give the C's out. And this is how many ways it can be done. How many ways the grouping can take place. On the other hand, if the groups are considered indistinguishable, then this number is an overcount. In fact, each grouping into indistinguishable groups corresponds to 3 factorial, or 6 groupings into distinguishable groups. And just to make that clear, here's an example. Suppose we identify the people as P1 through P12. This is one grouping into indistinguishable groups, so I didn't label these sets. P1 through P5, there's 5 of these, 4 here and 3 here. Actually, you have to ignore the order in which these are written, otherwise that would be an external way to distinguish them. So there's no way on a piece of paper I can write down these 3 groups without giving them some sort of distinguishing features based on their location on the page. Even if I put these in a circle, you could say, well, the leftmost or the topmost, there would be ways to, in general, to distinguish. So you have to kind of use your imagination here and pretend these 3 sets are floating in space and they're moving around, and there's no way to identify any of the sets by location. So this grouping into indistinguishable groups produces these groupings into distinguishable groups. And what I did here, to try to make this as clear as possible, is I left this group in this column. I didn't move the groups around, I moved the labels around. So I labeled this G1, G2, and G3. Here I kept the same label G1 for this, but I switched the labels. So this is G3 and this is G2. I could have, reversed these two. So all these were G1, all these were G2, and all these were G3. But I think this is more readable. It doesn't matter. You can do either way. But the point is that this single grouping into indistinguishable groups produced these groupings into distinguishable groups, and they correspond to the permutations of the index set, 1, 2, 3, 1, 3, 2, so on. So that's why there are 3 factorial, or 6 of these. So in summary, if we consider the groups as distinguishable, we get this number, 27,720. But if we consider the groups to be indistinguishable, we have to divide that by 3 factorial, and we only get 4,620. So in this case, even if we want the indistinguishable groupings, it was a good idea to compute the distinguishable groupings first and then divide, rather than have to figure out a way to go directly to the groupings into indistinguishable groups. This situation is going to come up, as I say, not only in this book, but in your further studies, that it's not clearly specified whether the groups are distinguishable or indistinguishable. If the context tells you clearly one way or the other, that's fine. If not, you're going to have to solve the problem in 2 different ways. There are literally hundreds of formulas involving binomial coefficients, because these coefficients are so important. And I wanted to show you a book I have. It's called Combinatorial Identities, written by Harold Gould. It is, I think, self-published. The copyright date is 1972. I acquired this book, I would say, in the mid-70s. This book contains hundreds of formulas involving binomial coefficients. It's a little hard to give you a good feel for this, as we are not in the same room, but let me just try to give you a sense of all these formulas. It goes on and on. There's some 100 pages of formulas involving binomial coefficients. I think this book is long out of print. Its best use, of course, is as a reference if you are looking for a particular formula. In any case, there are a few formulas, 5 in particular, that you do need to know. And they're given in this theorem. The first one is what I call mirror symmetry. I don't know whether that's a common term or not, but it seemed like a reasonable term. N choose k is equal to n choose n minus k. The most famous formula involving binomial coefficients is Pascal's formula. N choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Before you get too upset about having to memorize these formulas, there is a rationale behind them, and once you see what that is, it'll be much easier to to duplicate. So don't panic yet until we've gone through the proof of these formulas. This is called the chairperson's identity. N times n minus 1 choose k minus 1 equals k times n choose k. This I referred to as the subset's identity. The sum of all the binomial coefficients with the same upper value n. So k sums from 0 to n is equal to 2 to the n. This is quite remarkable. Over here you have a bunch of factorials of all sorts, and somehow they all coalesce together and end up a power of 2. And then, of course, the well-known binomial formula, which I presume you already know. Proofs of formulas that involve binomial coefficients are generally one of two types. An algebraic proof is a proof that just uses the formulas for binomial coefficients. N choose k is equal to n factorial over k factorial times n minus k factorial. So you can write out, for example, this first equation, write it out in terms of factorials on both sides, and you'll see that there is a bunch of cancellation. In fact, everything is going to cancel. So these two are in fact the same. You can do similar things here and here. Write the binomial coefficients in terms of factorials, do a little algebra, and you'll see that the equations are true. This one, I don't think that's going to work. You can try it. If you find a way, let me know. And this one, too, is not going to be very helpful to write this as n factorial over k factorial times n minus k factorial. That's not really getting you anywhere. So sometimes an algebraic approach will work and other times it won't. An alternative is what we call a combinatorial proof. And that's a proof that shows that both sides of the equation count the same thing. Then they, of course, have to be equal. When both types of proofs work, a combinatorial proof is generally preferred because it gives much more insight into what's going on in the formula, why the formula is true, where it came from. It didn't just pop out of the blue. It came from some reasoning, and that reasoning is critically important. Okay. So let's take a look at, I'll leave you to ponder the algebraic proofs for the most part, and let's look at combinatorial proofs. For this first one, we have to somehow reason that the number of ways of choosing k objects from a set of size n is the same as the number of ways of choosing n minus k objects from, say, the same set. Well, this is straightforward. There's two ways you can pick a subset of size n, of size k from a set of size n. You can pick what you want and keep it, or you can pick what you don't want and throw it out. This is the number you would get if you just picked k elements directly. This is the number you would get if you picked n minus k elements and threw them out. So these count the same thing. They both count the number of ways of choosing k elements from a set of size n. It just depends on whether you want to take, let's say, the optimistic point of view and just grab what you want, or the pessimistic point of view and grab what you don't want and throw it out. And this is a reasonable scenario. Suppose you had, say, a basket full of 1,000 golf balls, and somebody came to you and says, yeah, I'd like to buy 998 of them from you. Would you take a second basket and move 998 balls from the first basket to the second basket and then give him that second basket? In other words, would you choose what you want and and put it in another basket, or would you simply reach in and take 2 balls out of the basket, stick them in your pocket, and say, here's your basket of 998 balls? No. The second choice is obviously much simpler. As to a combinatorial proof of Pascal's formula, again, n choose k counts the number of ways of forming subsets of size k from a set of size n. So let's say this is what the set looks like. Now, notice there are 2 terms on this side. So we're looking for a way to split the process of selecting k from n into 2 mutually exclusive parts. Do it this way or do it this way. Well, one way to do that is to single out the last element, xn. Every subset of size k taken from this set either contains xn or it doesn't. So we can split the subsets into 2 pieces. They're disjoint pieces, and that will cover all possibilities. So if we can count the number of subsets of size k that don't contain xn, and we can count the number of subsets of x of size k that do contain xn, we just take their sum. The number of subsets of x that don't contain xn are simply the number of subsets of the set x1 through xn minus 1. And there are n minus 1 choose k ways of constructing those sets. Sets of size k that don't contain xn. So you ignore xn, you have n minus 1 elements left. Choose k. On the other hand, to form a subset of size k that does contain xn, what we can do is temporarily ignore xn. This time from the other n minus 1 elements, choose only k minus 1, and then throw in xn to get the kth element. So there are n minus 1 choose k minus 1 ways of doing that. And there's 2 binomial coefficients. You add them together, you get n choose k. Every time you can think of a way of splitting up the process of choosing k elements out of a set of size n into pairwise disjoint possibilities that covers all the possible ways of choosing k elements, you will get a formula involving binomial coefficients. Let's look at this chairperson identity. How do we know these 2 sides count the same thing? Well, the reason it's called the chairperson's identity is the following scenario. Suppose you have n people, and you must choose a committee of k people from those n. And you also need to select one of those k people to function as chairperson for the committee. There's 2 ways you can do that. You could choose the chairperson first from among all n people. There are n choose 1 or n ways to do that. Excuse me while I take a sip here. My herbal tea. After choosing the chairperson, you can turn to the other n minus 1 people and pick k minus 1 of them to fill out your k-person committee. Alternatively, you could first pick the k people for the committee, which can be done in n choose k ways. Then from among the k people you've chosen, you can pick one to be chairperson. That's K choose 1, which is written as K. So these two expressions count the number of ways of forming a committee of K people with a chairperson. The subset's identity is not amenable to an algebraic proof, as far as I know. So we'll turn to the combinatorial proofs. How do you justify that both sides of this count the same number? Well, I'm going to leave that for you. The 2 to the n is, you may recall, counts something very important with respect to subsets. And once you figure that out, the rest may be straightforward. Okay? But this is good practice in trying your skill at constructing a combinatorial proof. It's about 2 lines long. The binomial formula. How to prove this? Well, I don't think you're going to find a purely algebraic proof or easily find a purely combinatorial proof, but we can mix the two a bit. And it would go something like this. First, write the quantity x plus y to the n out this way, n factors, each of which is equal to x plus y. Now we want to expand this into a sum. And we so need to look at the terms that we're going to get from the expansion. Well, they're all going to have the form x to a power, so x to the k, y to the n minus k. Because what we need to do for the expansion is for each factor we choose an x or we choose a y. If we choose k x's, we multiply those together, then we have n minus k y's. Multiply those together, we get a term that looks like this. But there are going to be many of these terms. How many? The number of ways of choosing k of these factors from which to extract an x. Once we've determined the x factors, so to speak, the y factors are automatically determined. So there are n choose k ways of selecting k of these factors to pick out an x. And that'll give you the term x to the k, y to the n minus k. So this is the total when we add up all the terms, x to the k, y to the n minus k, we'll get this. Then we just sum on k from 0 to n, and that is precisely the binomial formula. Let's look at some more examples of counting techniques. It's surprising how quickly these numbers can get big. Factorials, as I mentioned before, can grow very quickly. So here's an example of where you might not expect the numbers to be quite so large. Suppose you're trying to arrange 100 photographs in an album, but there's only room for 95 photos. How many ways can you fill the album? Well, the first thing you should notice is it's not clear from the question whether it matters what the order of the photographs is. So since we're lacking that information, we need to solve this problem in both ways. If the order in which you place the photos in the album does matter, then we are talking about a permutation of size 95 taken from a set of size 100. And the formula looks like this. This is 100 lower factorial 5, and it works out to be roughly 8 times 10 to the power 155. This number is a monster. It is far greater even than the best estimates we have for the total number of atoms in the universe. That estimate's somewhere around 10 to the 80. So this number is gigantic. On the other hand, if the order in which you place the photos in the album doesn't matter, then we're dealing with combinations, so subsets of size 95 taken from a set of size 100. It's this binomial coefficient. Rather than deal with this, use mirror symmetry. It's 100 choose 5, which is 100 lower factorial 5. That's P105 divided by 5 factorial. That comes out to be a mere 75 million and change. So there's a dramatic difference between these two numbers, both of which seem quite large when you first think about this problem. One of the morals here in this solution is you must, if it's not made explicit, you must consider both the cases where order matters and where it doesn't matter.